we're going to talk about polyprotic acids. Polyprotic acids have 2 or more hydrogens on them. So this is sulfurous acid. It starts with H2. It's a diprotic acid. You can also have 3. So when these ionize, those hydrogens come off one at a time in separate steps. So the first step is for this to lose 1 hydrogen, and that leaves us with a hydrogen sulfite ion, and this has an equilibrium constant. This HSO3 minus has a hydrogen. It can lose that hydrogen as well, leaving us with sulfite ion. That also has an equilibrium constant. The second one is much smaller than the first one. First one here, 10 to the minus 2. The second one, 10 to the minus 8. That's 6 orders of magnitude. That's big, big difference. And this makes sense if we think about it, because when the proton is leaving this is a neutral molecule. Here, when the proton is leaving, it's leaving a negatively charged ion, so it's harder for it to leave, okay? So the first one is the biggest, the second one's much smaller, and if there's a third one, that's even smaller. These are some examples of polyprotic acids. Sulfuric acid, heard of that one. Phosphoric acid, this is triprotic. So sulfuric acid, diprotic, but over here where they list Ka1, 2, and 3, for Ka1 it just says strong. Because sulfuric acid, the first hydrogen ionizes completely. The second one is a weak acid, and so it has an equilibrium constant. Phosphoric acid, you see we've got 3 of them. So those are some polyprotic acids and their ionization constants. So how do we find the pH of a polyprotic acid solution? The first Ka is much larger than the second or third, and so the amount of hydronium ion formed in that first ionization is the most important. And many times we can ignore the second or third ionization. The formation of hydronium in that first step inhibits formation in the second step, Le Chatelier's principle. So we can treat most polyprotic acids as if the first step were the only one. One exception that's important. Dilute solutions of sulfuric acid. If we look at this, it's strong in its first ionization. The second ionization has a Ka of 10 to the minus 2, which is relatively large for weak acids. So, and we'll see an example of that. Okay, let's find the pH of a 0.050 molar carbonic acid solution. We're given Ka1 and Ka2. So the first thing we do is write an equation for the acid ionizing. Okay, so then we make an ice table, right? So initial concentrations. We're given the concentration of the polyprotic acid, so 0.050. And what do we know about the concentration of the hydrogen ion before this ionizes? It's almost 0. It's 10 to the minus 7. So we're going to call that 0. And is there any hydrogen carbonate ion in this solution before the acid is added? No. So that's because you can't go below 0 in concentration. Then we add those 2 rows together. And then what do we do? Anybody?
Find X.
Find X, yeah. So we can find X using the equilibrium constant. So write the equilibrium constant expression. So this is Ka1, just the equilibrium expression for that equation we wrote. Right? And then we have expressions for the equilibrium values of the concentrations. So we're going to substitute those in here. And we know what Ka1 is, so we're going to put that in over here. So Ka1, 4.3 times 10 to the minus 7. And that's going to equal the hydrogen ion concentration, X, times the hydrogen carbonate ion concentration, which is also X times X, divided by the H2CO3, 0.050 minus X. Any questions about that? We haven't done this a bajillion times, but we've done it a lot of times, right? And that tells you this is an important thing to know how to do. Okay, so we've got an equation with one variable. We're going to solve for X. We can try X is small, or we could use the solver on the calculator. I don't care which one you do. I like the solver better because then I don't have to check to see if it's less than 5%. So I'm just going to use my solver. If you want to do X is small, go right ahead. No problem with that. So if you use X is small, when you find X, you're going to look at your equation and see where X was added to or subtracted from a number. And you're going to divide it by that number. Because what we're saying is that if X is 5% or less of this number, then subtracting less than 5% is not going to matter. So I'm getting 0.0001464. Now, what did they say about finding the pH of a polyprotic acid? That usually you can ignore the second one, right? So if we ignore the second one, we've got this X. This X is equal to the H plus concentration. H plus at equilibrium is X. So then the pH would be the negative log of that. .8344. And 2 sig figs seems appropriate, 3.83 for our pH. This is a problem where we have the answer given to us so we can see if we did it right. And this, in fact, is the correct pH. Any questions?
second was bigger, the second Ka was bigger
The,
than
the,
first,
s-
what would
the
we do
second
instead?
Ka can never be bigger than the first. If it was really close, then you might have to consider it. Usually that doesn't happen though. But in the next slide, we're going to do a dilute sulfuric acid solution, which is one where we do need to look at that. Any other questions about that example? So here we're asked to find the pH and the sulfate ion concentration of a 0.0075 molar sulfuric acid solution. And they're giving us Ka2. They didn't give us Ka1. Why?
Is it smaller?
Pardon me?
Is it because it's smaller?
No,
Strong acid.
it's a strong acid. So the first one is strong, and so we don't have a numerical value for it. It just ionizes completely. So I guess you could think of it as infinity if you wanted to. So sulfuric acid, the first ionization is complete. So we get H plus H SO4 minus. The second ionization will be HSO4 minus, ionizing to form H plus and SO4 2 minus. This one could be a little tricky to remember, but a clue is they don't give you Ka1. And it's not just that we made a typo and forgot that. It means something. So this one goes complete, right? So then we're essentially using stoichiometry to figure out what happens in this first one. So if I initially have 0.0075 molar H2SO4, maybe we'll do initial and final. After it finishes, what's the hydrogen ion concentration going to be? 0.0075. And this is going to be 0, and this is also going to be 0.0075. There's other ways to think about it, but does everybody understand that okay? For every mole of sulfuric acid that we have per liter, we get 1 mole of hydrogen. We get 1 mole of hydrogen sulfate. And so the concentrations here are the same as the initial concentration. It came apart. So we're going to do an ice table with our weak acid over here. So the initial concentration of HSO4 minus, it's not going to be, well, it is going to be this number, but where does this come from? It came from that, ionizing, right? So that's going to now start out at 0.0075. It's a bad 0. What's the initial concentration of hydrogen? 0.0075. It isn't 0 because the acid ionized already, right? So now the concentration of hydrogen ion is not 0. How about the concentration of sulfate ion?
0.
That's 0. Okay, so here we've got our ice table. This is going to be minus X plus X plus X. And then Ka2 equals the products over the reactants for this reaction. So we write the equation, chemical equation, we make the ice table, we write the equilibrium constant expression, and then we substitute in values for the things in there. So we know what Ka2 is. It's 1.2 times 10 to the minus 2. And X would be 0.0075 plus X. And sulfate is X. And hydrogen sulfate is 0.0075 minus X. This is the sort of setup where doing X is small makes the math super easy. Because if this is 0 and that's 0, then we've got 0.0075 on the top and the bottom. Those cancel out, and X is just the equilibrium constant. But we have to check and make sure. So let's take that equilibrium constant, 1.2 times 10 to the minus 2, and divide by the 0.0075. 160%. Not small. Not even close to small. This is a relatively large equilibrium constant, and this is quite a small concentration. So X is small, doesn't work there. So we do need to do the number solver. X equals 0.003854. The equilibrium constant is 0.0012. And so here X is actually larger than the equilibrium constant. So we need the pH at equilibrium. Yeah, question?
So we have hydrogen in the solution already from the first one, right?
Yeah.
And so what if is it possible to take that one and just like do them separately and then add them together at the end? Like add the X stuff?
That's exactly what we're doing.
That's what we're doing, but we're including the X as well.
Yeah, so the question is, can we take these hydrogens, do them separately, and then add them together? Yes, so what we have here, at equilibrium, this will be that number plus X.
Oh yeah, you're right. Okay.
So it actually works out. That's exactly what we're doing.
Okay.
Good job. So X equals what? The hydrogen ion concentration? No. It equals the sulfate ion concentration. And that was one of the questions, right? They wanted the sulfate ion concentration. So we'd probably do that as 3.9 times 10 to the minus 3. And so the hydrogen ion concentration will be the 0.0075 plus 0.003854 0.011354. We actually gained a sig fig there because when you add numbers, you look at how many decimal places. This one has 4 decimal places with 2 sig figs. This one has 4 decimal places. And so this one's going to have 4 decimal places, but now it has 3 sig figs. And that's okay. So pH is the negative log of that. .9448. We'll call that 1.945. Let's put that guy in there too. Any questions? When we look at the answers given in the book, they've got 3 decimal places in the pH. I agree with that. They've got 3 sig figs in the concentration, and I would argue with them about that, but we're not going to worry about it. So we may want to know not just the pH of this polyprotic acid, we might want to know what the concentrations of the anions are. So here's our diprotic acid with its first ionization to make HX, and here's the second one to make X2 minus, 2 equilibrium constants. So to find this concentration, we're going to just do an ice table with this and find out what the hydronium ion concentration is, and HX minus will be the same. To find X2 minus, we're going to have to take this number, and those are going to be the initial concentrations in our second ice table, which is just like what we did with sulfuric acid. So this says, find the carbonate ion concentration of the 0.05 molar H2CO3 solution from that other example. And through the magic of computers, there it is. So what I'm going to do is I'm going to copy this. Not up there. That doesn't copy. And paste it in. To do this problem, to find the carbonate ion concentration, you have to do 2 ice tables. And to save us time, they already had us do the first one in a previous question. So we found X, and X was equal to the hydrogen ion concentration. We found out that the pH was 3.83. So now we're going to look at the second ionization. So the second ionization is HCO3 minus in equilibrium with H plus and CO3 2 minus. The initial values here are going to come from what we ended up with over there. because this happened first, and now the hydrogen ion concentration is equal to X. So the hydrogen concentration is going to be 0.0001464. And the carbonate, sorry, the hydrogen carbonate, the hydrogen carbonate is going to be the same. Everybody okay with that? This is different. When we did the sulfuric acid, the first step was complete, right? And so we weren't really looking at an ice table to get initial concentrations. Here, the first step is weak, and so we use the first ionization constant to find out how that ionizes. This X is the hydrogen ion concentration when the second one starts. And HCO3 was also equal to X, and so that's now our reactant. What's the carbonate ion concentration before this one gets going? 0. Any questions about that? That's the hardest part in a problem like this. So now we do our X's again. Plus X's. Oh, that one's not plus. This one's minus. And so this number is annoyingly long. So that's one thing. So those are our equilibrium expressions. Write the equilibrium constant expression for Ka2. It's going to be H plus times CO3 2 minus divided by HCO3 minus. I'm getting this from the equation up here. And now I'm going to take what I wrote in the equilibrium row, and I'm going to plug those things in for these concentrations. I'm going to take the given Ka2 and plug that in there. So they told me Ka2 was 5.6 times 10 to the minus 11. And this is going to be on the top 0.0001464. I lost a 4 somewhere. And that one's plus X, that quantity times X, divided by that same stupid number. I'm tired of that number. I already saw it too many times. I didn't like it yesterday.
What makes us think like
Could put it in scientific notation, but in 3 zeros, it doesn't really help. So everybody okay with how I got that? Yes.
So why is for the change for the H plus, why is it plus X?
That's a good question.
It's getting more.
So why is this plus X? So this equilibrium can go to the right or to the left, right? And so if it goes to the right, both of these are going to go up. If it goes to the left, both of these are going to go down. One of them's at 0, so it can't go down. Any other questions? Well, this looks more like X is small might work, because this is a very small equilibrium constant. So X is small says, well, this X is essentially 0, and this X is essentially 0. And then ugly number cancels out, x equals 5.6 times 10 to the minus 11. We need to check and see, is x small enough? 5.6 times 10 to the minus 11. We're dividing by the number we're adding or subtracting it to. 0.000146 times 100. And we get 4 times 10 to the minus 5%. That's super small. So I'd be... What were we trying to find? The CO3 2 minus. That's what X is. So that's our carbonate ion concentration. So that's the answer we were looking for here. And just for funsies, let's see what would happen if we go ahead and calculate the new hydrogen ion concentration. The new hydrogen ion concentration would be 0.001464 plus, so if we add X on there, it doesn't make any difference. So this is why when we're finding the pH of a polyprotic acid solution, we can just look at the first one, because the second one is going to be so small it doesn't matter, except for dilute sulfuric acid. Any questions? Here's just looking at the dissociation of a polyprotic acid. It's a diprotic acid. We have the first ionization, and here they've done all the math for us, weren't they kind? 2.8 times 10 to the minus third. And the second ionization now starts with H3O plus being bigger than 0. And so that causes this equilibrium to not go as far to the right. It causes it to produce less hydrogen ion. So it inhibits the amount produced. So then the total, you add those two together, and we see that that second one was so small it didn't matter. So if you're looking for the concentration of the anion, like we were for carbonate, CO3 2 minus, here we've got C6H6O6 2 minus. That concentration is just going to be equal to Ka2. That works when the X is small, approximation is valid. If you forget that, maybe you have to calculate that on a test, you forget it, you can do the ICE table, you'll get the right answer, and then you'll go, oh, that's right, it was just K. No harm done. Any questions?